So we are now ready to go through the full unit circle. We've essentially done this already in the first quadrant, and we've utilized this when we talked about finding sine and cosine and other trig function values at different angles, utilizing that reference angle. So what we want to do is we want to spend a lot of time focusing on just building the unit circle, because this is something you're going to need to know. You're going to need to be able to evaluate it, and it's just going to take more and more practice to become fluent in this. Because moving on to the calculus sequence, you heavily use trig. It does not go away. So these functions and knowing when these functions equal certain things is going to be important for us. So if you can build the unit circle in the first quadrant, you are going to be able to build it for every other quadrant. And this is going to help you evaluate sine, cosine, tangent, and all of the reciprocal functions by just a picture, okay? So we're gonna start by building that important table. We've already done this in degrees, but now we're gonna do this in radians and refresh. We have a few main angles in that first quadrant from those special reference angles: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and then our first quadrant ends at 90. We want these in radians as well, so we have 0 radians. 30 degrees is pi over 6, so remember it's the opposite number. 45 degrees is pi over 4, and 60 degrees is pi over 3. And then last but not least, 90 degrees is pi over 2. We need to know what sine of these angles are, what cosine of these angles are, and that in turn is going to lead us to tangent, because tangent is sine of the angle over cosine of the angle. So again, that order is important. For sine, we start by putting a 0 in the corner, and then we go up by 1 until we get to 4. So remember, to find sine of 0, I just take the square root of this number and divide it by 2. So I'm just going to do this for the first one. Square root of 0 divided by 2 gives you 0. Sine of 30 degrees, or pi over 6, is square root of 1 over 2, which just gives you a half. This one is root 2 over 2. This is root 3 over 2. And then that gives you root 4 over 2, which is 2 over 2. So this simplifies to 1. Now to do cosine, you really are just going to flip this row, which is the same thing as starting at 4 and going down to 0. So everything goes backwards. This is 1. This is root 3 over 2, root 2 over 2, 1/2, and finally 0. To find tangent, you just take sine divided by cosine. So that's 0 over 1. Tangent of 0 is 0. When it comes to these where you have denominators, because they're all the same in both fractions, they cancel each other out. So really you just end up with those numerators. 1 over root 3, which rationalized would be root 3 over 3. Dividing by these is the same, and then here you get root 3 over 1, which is root 3. Unfortunately for this last one, when you try to take 1 and divide it by 0, tangent of 90 degrees, or tangent of pi over 2, is undefined, okay? So our unit circle, anytime you hear the word unit, it's going to indicate something important involving 1. So the unit circle is a circle of radius 1. So our formula for a circle, remember, is x squared plus y squared equals the radius squared when it's centered at the origin. So in this case, just x squared plus y squared equals 1. So what we're going to do, if I look at any point on this circle, it satisfies that equation, x squared plus y squared equals 1. And the distance to that point is the radius, which is 1. So if I go ahead and I draw a right triangle in here, this would be my y value, this would be my x value, and that is that right angle. or sorry. And then this is the angle theta, which is found by going up to that terminal side. Okay. So for any triangle we draw in here, the hypotenuse is going to be 1. So what that means is if I take cosine of whatever this angle is, that is the adjacent over the hypotenuse. So that is x over 1, which is just x. And then same thing with sine. Sine of the angle is opposite over hypotenuse. So y divided by 1 is just y. So what happens is these xy coordinates are just found by taking cosine of the angle and sine of the angle. So my x coordinate is going to deal with cosine, and my y coordinate is going to deal with sine, okay? So the points on the unit circle tell you cosine of the angle and sine of the angle, purely because we picked that radius to be 1. So we're gonna go ahead and we're gonna build the quadrants, or build the unit circle in each quadrant. So I'm gonna start in quadrant 1 and we're gonna go ahead and build the unit circle there. So ultimately I have 3 main angles, not including the quadrants themselves. The first angle is going to be here at 30 degrees. Then the next angle's at 45. The last angle is at 60, okay? So within each of these, I'm gonna end up drawing a right triangle. My first key angle is 30 degrees, which is also pi over 6. My next key angle is 45 degrees, which is pi over 4. And my last angle is 60 degrees, which is pi over 3, okay? So if I look at cosine of 30 degrees, you can go back, you can utilize your chart, but cosine of 30 degrees is root 3 over 2. And then sine of 30 degrees, or in this case, if I use the radians, this would be 1/2. So this point here on the end of my unit circle would have the coordinates x and y. It's root 3 over 2, 1/2, okay? So this tells me cosine of this angle. This tells me sine of this angle. Then moving on to 45 degrees, I look at cosine of 45 degrees. That is root 2 over 2. And then sine of 45, again, I'm going to use the sine in those radian forms. This will be root 2 over 2. So this point here on the unit circle would have the coordinates root 2 over 2, root 2 over 2. So now I know what sine and cosine of this particular angle are, and then I can also utilize that to find tangent and to find my reciprocals. Then my last one, in the first quadrant at least, is 60 degrees. If I look at cosine of 60 degrees, that's going to be 1/2. And then sine of 60 degrees is root 3 over 2. Or again, you can use the radian angle. So this point here on the unit circle would have the coordinates 1/2 root 3 over 2, okay? Now if I want to find the angles in different quadrants, you're really just going to be reflecting stuff. Because remember, there's really nice symmetry in your unit circle. So if you go ahead and flip this to the other side, the values are not going to change, just the sign on x will. So in this case, in quadrant 2, the cosine values are going to become negative. But in quadrant 2, sine is positive. So try to keep this on the screen still. I still have those 3 key angles. There's a 30-degree reference angle, a 45-degree reference angle, and a 60-degree reference angle. And that in turn is going to be how we make that reference triangle to find sine, cosine, and all of these angles. So here, the reference angle would be 30 degrees, 45 degrees, and 60 degrees. I'm going to use degrees for the rest of these, and then when we actually build the full unit circle in one, I'll show you how to find the radians as well. But here, my actual angle that I'm working with then, considering the positive case, would be I go 30 degrees back from 180, so this would be 150 degrees. So again, the points here do not change value. It is still going to deal with root 3 over 2 and a half. But because I'm in quadrant 2, my x value is negative, because I really just reflect this over based on symmetry. So what this tells me is when I look at cosine of 150 degrees, it is equal to the x coordinate, which is negative root 3 over 2. And then sine of 150 degrees is the y coordinate, that is 1/2, okay? Looking at the 45-degree reference angle, then this angle here would be 180 minus 45, that is 135 degrees. Nothing changes from the values up here, but x is negative. So this would have coordinates negative root 2 over 2, positive root 2 over 2. So that tells me cosine of 135 degrees would be negative root 2 over 2. Sine of 135 degrees is the y coordinate, which is positive root 2 over 2. And then again, realistically, if I go around more revolutions, as long as my terminal side lands here, you still use the same coordinates to get sine, cosine, tangent of that angle. Then our last step is our 60-degree reference angle. So that means the actual angle we're looking at is going to be 180 minus 60. So that is 120 degrees. The coordinates again stay the same, but the x value is negative. So this would be negative 1/2, positive root 3 over 2. That tells me cosine of 120 degrees is negative 1/2, and sine of 120 degrees is root 3 over 2. And it's always good, especially when we start getting more complicated, to put parentheses around the angle. Not necessary though in this particular case because it's pretty clear. It's just when we have more stuff. When we move to quadrant 3, well, what's going to happen is this image just gets flipped over the x-axis. So in that case, quadrant 3, both x and y are negative. So the only thing that's going to happen when I flip that point down to get the reverse image is now your y coordinate also becomes negative. So I'm still concerned with those same 3 angles, 30 degrees, 45 degrees, 60 degrees. Got our triangle here with that reference angle of 30. We've got our triangle here with that reference angle of 45. And then our last triangle here with a reference angle of 60. So again, my point here, the numbers do not change. They're just both negative now. So the angle I'm looking at would be this full one starting at 0. So you go forward 30 degrees after 180. That would be 210. Okay. So this tells me that cosine of 210 degrees is negative root 3 over 2. And sine of 210 degrees is negative a half. Moving on to 45, these would just both be negative. 45-degree angles give you sine and cosine being root 2 over 2. So this particular angle will be 180 plus 45 more, which is 225 degrees. So cosine of 225 degrees is negative root 2 over 2. And sine of 225 degrees is the same thing, negative root 2 over 2. Moving on to the 60-degree angle. Again, these numbers don't change. Cosine of 60 degrees is a half. Sine of 60 degrees is root 3 over 2. And because we're in quadrant 3, they are both negative. This particular angle would be 60 plus 180. So this is 240 degrees. So cosine of 240 degrees is negative half. And sine of 240 degrees is negative root 3 over 2. Okay. Going on to our last quadrant, you again can just go ahead and flip these over, or the other way you can think about it is these flip down. So either way, what happens in quadrant 4 is your x is positive, but your y is going to be negative. So all of the sine values become negative. So looking at our three main angles, here's 30 degrees, 45, and 60. Draw in our lovely little reference triangles and fill in those numbers. 30 degrees, 45 degrees, and 60. I'm going to go ahead and just fill in these points as well while I'm at it for all three. So again, my x is now positive, so a 30-degree reference angle gives you cosine being root 3 over 2. Sine would be a half, and since it's in quadrant 4, sine is negative. At this point, 45-degree reference angle is they're both root 2 over 2, but your y value is negative here. And then dealing with 60, your cosine is a half, your sine is root 3 over 2, and then that one will be negative. The actual angle would be this total angle is 360, but I need to go back 30 degrees. So 360 minus 30 gives me 330 degrees. So using that unit circle then, cosine of 330 degrees is root 3 over 2. Sine of 330 degrees is negative a half. For this angle again, it would be starting here and ending here. Full thing is 360, going back 45 would be 360 minus 45. So this particular angle is 315. So cosine of 315 degrees is the x-coordinate, and sine of 315 degrees is the y-coordinate. Then last up, we have the 60-degree angle. So 360 minus 60 means this reference angle, or this particular angle, is 300. So that tells me cosine of 300 is the x-coordinate, which is a half, And then sine of 300 is the y coordinate, which is negative root 3 over 2. Okay. Then from here, you can either convert these to radians, but I'm also going to show you how to do that just on the unit circle itself. So again, we haven't really done anything other than find sine, cosine of each of these values. But again, building this unit circle is really important because it helps us evaluate tons of different angles. Because now we're going to go through and we're going to build this entire thing piece by piece. But the idea is if I have an angle that's outside that 0 to 360 or the 0 to 2 pi range, I just need to see where does it end up falling on the unit circle, okay? So we're going to go ahead and we're going to build it again quadrant by quadrant, and that'll help us. You likely, to do your homework and everything, either want to have a unit circle up on the computer, but I would highly recommend at the start of all your homeworks at this point, maybe print out a bunch of blank copies or draw some circles with these different markers on it, but practice just building the unit circle. Again, I cannot stress enough, you cannot rely on your calculator to find these values. You need to be able to build this unit circle, okay? So again, we're gonna go through the first quadrant and then we're just gonna use symmetry of a circle. So starting out, this first angle here would be 0, but also that's a full rotation around. You come back to 2 pi. So this point on the unit circle is important for us. It is 1, 0. Cosine of 0 is 1. Sine of 0 is 0. Cosine of 2 pi is 1. Sine of 2 pi is 0. So this still tells you those angles and sine and cosine there. When we come up here, this angle would be pi over 2 or 90 degrees. And that coordinate would be 0, 1, okay? So cosine of 90 degrees is 0, sine of 90 degrees is 1. Then we hit, I'm gonna do everything in degrees first, and then we'll go through with radians. So we hit all of those main angles. The first angle we hit is 30 degrees. The second angle is 45 degrees. And the third angle is 60. So again, there's really nice patterns to it. It's 30 plus 15 plus 15 plus 30. Same thing's gonna happen. Plus 30 plus 15 plus 15 plus 30. So that symmetry is always gonna work out. 30 degrees is the same thing as pi over 6. 45 degrees is pi over 4. And 60 degrees is pi over 3. This point on the unit circle deals with sine and cosine of 30 degrees. So cosine of 30 is root 3 over 2. Sine of 30 is a half. When they are the same, 45 degrees, both outputs of sine and cosine are root 2 over 2. And then when we get to the 60-degree angle, it is just going to be the flip of this. So that is 1/2 root 3 over 2, okay? Now I'm gonna go ahead and I'm gonna fill in the second quadrant. This angle over here would be 180 degrees, which is the same thing as pi. So this particular point is -1, 0. So any angle that lands here is going to have your cosine be -1, your sine be 0. Likewise, any angle that ends up here is going to have your cosine be 1/2, your sine be root 3 over 2. Okay? Now to get these particular angles, I'm going to start by filling in the actual coordinates. These just flip over, okay? And when it goes in quadrant 2, your x value turns negative. So up here, it's the same as this one, but your x is now -1/2. This has them both with the same value, root 2 over 2, but your x is negative. And then this point down here has x value negative root 3 over 2, and your y is positive a half. Okay. Now I want to figure out what is that main angle between 0 and 360 that deals with this. So again, I'm going to start by doing it with degrees. So to find this full angle, we have to go back a reference angle of 60. So from 180 degrees, we need to go back 60, which means this angle is 120. So sine of 120 and cosine of 120 are just found by that point, but I said it backwards, okay? But I also want this in radians, so instead of going back 60 degrees, I want to start at pi, and I'm going to go back that in radians, which is pi over 3. So from pi, we are going back pi over 3. So hopefully you can deal with these fractions, but that's 3 pi over 3 minus pi over 3. This angle in radians is 2 pi over 3. So cosine of 2 pi over 3 is negative a half. Sine of 2 pi over 3 is root 3 over 2. This middle angle deals with a 45-degree reference angle. So again, from 180, we are going to go back 45 degrees, which lands us at 135 degrees. You can then convert that to radians, but if you don't have a calculator, you can't do that real easily in your head. So again, the easiest way is this total is pi, and we're going back 45 degrees, which is pi over 4. So from pi, we are going back pi over 4. So that would be 3 pi over 4 when you simplify it. Then last up, to find this particular angle, we have a 30-degree reference angle. So again, you can see that pattern. From 90, you went up 30, 15, you're gonna go up 15 again. But from the full straight angle, we go back 30 degrees, which means this is 150. And then the same thing, this full angle is pi. Going back 30 degrees is pi over 6. So from pi, we remove pi over 6, which you can then fill in, that's 6 pi over 6. So this gives us 5 pi over 6. Okay. Now to go in quadrant 3, I just go ahead and flip these down. Again, this now makes your y value negative. So when I flip this across, that's my first one. So this point here would be negative root 3 over 2, negative a half. This one here would both be negative, negative root 2 over 2, negative root 2 over 2. And again, this one is just the flip. This is negative a half, negative root 3 over 2. And now I need to find each of these angles in both degrees and in radians. So starting out with this first angle, which would be this total distance, from 180, we go 30 degrees forward. So this would be 210 degrees. So cosine of 210 is negative root 3 over 2. And then sine of 210 is negative a half. To deal with radians, we go pi plus 30 degrees, which is pi over 6. So again, you can make this over 6 if you want, but this is 7 pi over 6. For a 45-degree angle from 180, we're going an extra 45 forward. So this is 180 plus 45, which is 225 degrees. But again, that's the same thing as saying we go pi, and then we go pi over 4 more. So to simplify this, write that with the same denominator. That gives you 5 pi over 4. And then our last angle, we go pi plus 60 degrees or plus pi over 3. So from 180, we go forward 60. This would give us 240. Or starting at pi, that would be plus pi over 3. And then again, make this with the same denominator. This special angle is 4 pi over 3. So again, just to reiterate what this means, this tells you cosine of 240 degrees is the x coordinate, and sine of 240, or this angle in radians, is the y coordinate. So you just use that point on the unit circle. So we are almost done. We are in that last quadrant and this last quadrantal angle. But again, just take this and you flip it over to get the last piece. This right here has the coordinates 0, -1. This is 270 degrees, which is the same thing as 3 pi over 2. Because it's halfway in between pi and 2 pi. So cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. I'm going to again start by filling in these points. So this first one here, we just flip this over, but now my x becomes positive. My y is still negative. This point is the middle one. They are both √2 over 2, but your y value is negative. And then up here, same numbers, but your x is positive, your y is negative. Now I need to find each of these actual angles. So I'm going to start with the first one. From 2 pi, we have to go back 30 degrees. Or from 360, go back 30. So this special angle is 330 degrees. Well, doing that in radians, 360 degrees is the same as 2 pi. So from 2 pi, we are going back pi over 6 radians. And again, 2 pi, you can convert that. That's 12 pi over 6 minus pi over 6. So this special angle is 11 pi over 6. For this angle, which is that middle one, that's a 45-degree reference angle. So from 360, we go back 45. So 360 minus 45 gives me 315 degrees. But doing this in radians, that's 2 pi minus pi over 4. Well, 2 pi, putting it with a 4 in the denominator would be 8 pi over 4 minus pi over 4. So this is 7 pi over 4. And then last but not least, from 360, we go back 60 degrees. Making this 300 degrees. Or from 2 pi, we go back pi over 3. Putting that with a 3 in the denominator is 6 pi over 3 minus pi over 3. So this special angle is 5 pi over 3. So that is our full unit circle. And again, when I get larger angles, All I need to do is figure out what is the reference angle and which quadrant it lands in. Once you have this though, you know sine and cosine of all of those different angles. So you then can use this unit circle to evaluate the other 6 main trig functions. Or again, any angle that ends up coterminal with one of them. There is one thing we do need to be careful of, and it's in these situations where one of these is equal to 0. Because when we're trying to find those reciprocals, you could end up dividing by 0. So we have to be really careful for reciprocal functions. So I'm going to start by introducing this idea of what the domains of each of these are. But if you think about tangent of theta, that is sine of theta over cosine of theta. And the other reciprocal function that has cosine in the bottom is secant. Secant of theta is 1 over cosine of theta. Both of these run into issues when cosine of theta is 0, because then we divide by 0. So these are undefined when cosine of theta equals 0. So if I go back to my unit circle, cosine of theta is going to equal 0, and we're going to zoom out on this, at these quadrantal angles. Okay, so 90 degrees, 270, pi over 2, 3 pi over 2. Or again, any angle that's coterminal with this. So basically, if you take pi over 2, try using a different color, and then you go 2 pi around, that would be pi over 2 plus 4 pi over 2, lands you at 5 pi over 2. Okay. So pi over 2 and 5 pi over 2 are coterminal. 3 pi over 2 is the odd one that's in between it. So if you add 2 pi to this, you would see it's 7 pi over 2. Then the next one would be 9 pi over 2, 11 pi over 2, 13 pi over 2. And then you can keep going around and around and around. And then you can also go the backwards direction. So really these angles that end up on the y-axis are going to be odd multiples of pi over 2. Okay? So this happens in particular when the angle is coterminal with pi over 2 or 3 pi over 2. So the easier way to think about this is it's going to be an issue when you have any odd multiple of pi over 2. Okay. So there is a set way we have to write that. The odd part's harder to write. But our domain for these two expressions is our theta value cannot be an odd multiple of pi over 2. So the way we can write an odd number is if you take 2 times an integer, that gives you an even number because it's divisible by 2, and then you add 1. So 2n plus 1 will always give you an odd number. If you plug in n equals 1, that'd be 2 plus 1, 3. Plug in n equals 0, 0 plus 1 is 1. N equals 2, 4 plus 1, 5. So that's always going to represent an odd integer, no matter what you plug in for n, as long as it's a nice number, okay? Then our other two reciprocal functions are something that has a trig function in the denominator, deal with sine in the bottom. So if you look at cotangent of theta, this is going to be cosine of theta divided by sine of theta. and cosecant of theta is 1 over sine. These are both undefined when the denominator is equal to 0. So that would be when sine of theta is 0, okay? Going back up to my unit circle for that, sine of theta is the y-coordinate. That's going to happen when we land on the x-axis. These are much nicer though, because this is 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. Really any multiple of pi. So this one's much nicer. This happens when the angle is coterminal with 0, pi, or 2 pi. So this is any multiple of pi. So the domain is much easier to write for this one. It's any multiple of pi. That is going to be when our function is undefined. So n pi, where n is any integer. So I know we just spent a ton of time building that unit circle. So I'm going to do my questions to just a minimum for this, because again, you just need to figure out if I have an angle where I land. This is cosine of the value. This is sine of that value. So you just figure out where the angle lands. There's sine, there's cosine. There are all 6 of your trig functions, okay? So we'll do a couple examples. Starting out, we're gonna find sine of negative pi over 3, cosine of negative pi over 3, and then we'll utilize that to find tangent of negative pi over 3. And then the other example we'll do is just very different in general, okay? So let's start by drawing a picture. If I'm looking at negative pi over 3, that is a backwards angle. And if you think about pi over 3, it is 60 degrees. So this would be 0 degrees here, 0 radians. This would be negative pi over 2. So negative pi over 3 will land somewhere here with that 60 degree reference angle. Okay. So I'm gonna look at the point on my unit circle that has a 60 degree reference angle. Okay. So again, I can go all the way back up here to find that, but negative pi over 3 would land me right here with these coordinates. But again, just utilizing that reference angle, my first coordinate on the unit circle is cosine of that angle. Cosine of 60 degrees is a half, and I'm in quadrant 4, so my x is going to be positive. Sine of 60 degrees is root 3 over 2, and I'm in quadrant 4, so that is negative. So now to evaluate sine of negative pi over 3, it's just the y-coordinate, which is negative root 3 over 2. Cosine of negative pi over 3 is the x-coordinate, which is a half. To find tangent, I just take sine and divide it by cosine. And again, these denominators end up canceling. So it's just negative root 3 over positive 1. So overall, that is negative root 3. Okay. So this one's not a terrible one because that angle itself, pi over 3, was pretty straightforward to convert. But in the next example, having it be 23 pi over 6, that's a little more difficult. However, again, I'm just going to focus on finding cosine of this angle, because remember, secant is 1 over cosine. So if I can find cosine of 23 pi over 6, then I'll know secant. So because I have a pi over 6, that tells me I have a pi over 6 reference angle. And really pi over 6, just to fill that in, because again, I know degrees are much easier for us to remember. It's the opposite number with the 3's and 6's. So pi over 6 is 30 degrees. Okay? So the output of cosine for a 30-degree angle will be positive root 3 over 2 or negative root 3 over 2. It just depends on which quadrant we fall in, okay? So we have to figure out, where does 23 pi over 6 fall? Okay. So I'm gonna go ahead and I'm gonna draw my full XY axes. I'm gonna need a little more space there at the top, so I do want to move this down. Okay. So I need everything in terms of radians. So I'm gonna start out with 0 radians. Then up here, this would be pi over 2. Now, the problem is I have to see what 23 pi over 6 is in between. So instead of using pi over 2, I'm gonna put it in terms of a 6 denominator. So you would times top and bottom by 3. This is going to be 3 pi over 6. This angle is pi, which is 6 pi over 6. Then down here is 3 pi over 2, which to get in terms of a 6 in the bottom would be 9 pi over 6. Okay. And then when I come back up here to 2 pi, that's 12 pi over 6. So really, if I make one full revolution around, that's 12 pi over 6. My angle, however, is 23 pi over 6. So it's bigger than one revolution. So I'm gonna go again around and see, can I figure out where 23 pi over 6 falls? So really, if you notice what's happening each time, you go up 3 pi over 6, 3 pi over 6, 3 pi over 6, 3 pi over 6. So you don't need to put the next one in terms of 3 pi over 2 if you don't want to. Just go ahead and add 3 pi over 6. So this is 15 pi over 6. Well, 23 still does not fall in between these, so let's keep going to see if it lands in here. This would be 3 pi, which again, just add 3 pi over 6 to this. That's 18 pi over 6. 23 still does not fall in between these. So go forward another 3 pi over 6. That would be 5 pi over 2 as a simplified angle, but that would be 21 pi over 6. And I'm closer now. I have 23 pi over 6 as my angle. So maybe it falls in this quadrant, but I'm gonna go ahead and do one more to see what this is equal to. So one revolution is 2 pi. Another revolution would be 4 pi, so you add 2 pi to it. But again, going forward 3 more pi over 6, 4 pi is 24 pi over 6. So finally, I now have 2 consecutive numbers that my angle is between. So 23 pi over 6 lands in this quadrant. So since I'm dealing with cosine in quadrant 4, cosine is positive. So using that reference angle, I know this is going to be the case now where my output is positive root 3 over 2. So that tells me then what secant of this angle is. We just flip cosine of 23 pi over 6. But if you flip that, you'd get 2 over root 3. But we don't like it with a radical in the bottom. So again, we need to go ahead and rationalize by timesing by root 3 over 3. So secant of 23 pi over 6 is 2 root 3 over 3. Okay. So again, it's just going to take a lot of practice getting used to these. Take your time, get comfortable with your unit circle. But we do have one more thing we're going to talk about in this section, since you kind of see we keep going around in these different angles. We've talked about arc length as well. So something that naturally comes up are two concepts of linear speed and angular speed. So starting out first with linear speed. This is denoted by a V. It refers to the change in position with respect to time of a point on the outer edge of a circle. Okay. So essentially the idea behind this is if you have a circle and you have a point that's moving along that circle, you're trying to find what is its speed. Okay. And you can think of this really just using your distance formula. Distance is equal to your rate times time. Kind of manipulating that your speed or your rate is going to be your distance over your time. And this is a formula we really end up using for both of these different concepts. So in our case, the way we denote speed is this linear speed, which is a V. Your distance in this case is traveled on the circle. So that distance is your arc length. And then your time is whatever time it's given to you. So we just use a T. Okay. Angular speed is a very similar concept, but you're trying to find the rate of change of your angle. So angular speed is denoted with an omega. I know it kind of looks like a W, but it is a Greek letter. So if you need to look that up, this is omega. But this is the change in theta with respect to time. And again, our theta is going to be measured in radians. So essentially, I'm trying to see if I map out an angle this big, this is my theta. Over a certain period of time, I want to see how fast I went. So using that same formula, speed is your distance over time. Your angular speed is omega. Your distance is the angle itself. That's how much was mapped out. So it is theta over time, okay? So one thing that does happen is there is kind of a simple formula that results from this as well. If I look at my linear speed, that is also related to how fast my angle's being created. So there is a nice connection between the two, because we know our arc length is written in terms of the angle. So our linear speed is equal to S over T. But our S can be found by taking the radius and timesing it by theta. And so what really ends up popping in here is theta over T is exactly our angular speed. So our linear speed is going to be our radius times the angular speed, okay? So we're gonna do just one example with multi-parts of this. We're gonna find these key components. But again, these formulas just come from your distance is equal to your rate times time. We just rearranged it, to just fill in that formula here, your distance is equal to your rate times time. So solving for your rate, you divide over by t, okay? So suppose point P is on a circle with radius 10, and ray OP is rotating with an angular speed of pi over 18 radians a second. We're gonna find a couple things. We're gonna start by finding the angle generated by P in 6 seconds. So if you do want a visual as to what's going on, we've got a circle here with radius 10. We have this point P at the end of it, which is rotating around in this direction, and that creates a ray. O is just the starting point in that center. So it is rotating around at a rate omega, which is going to be pi over 18 radians per second. Okay, so that's how this ray is moving. So I want to first find the angle generated by P in 6 seconds. So my omega, which is my angular speed, is equal to theta over time. I want the angle though, so theta is going to be my speed times my time. My distance is my speed times time. So the angle is pi over 18 times 6, because that's how long this is going for. And then dividing those, 6 over 18 simplifies to pi over 3. So our angle is going to be pi over 3. Okay. So after 6 seconds, this will create a 60-degree angle moving at that particular speed. Next up, we want to find the distance traveled by P in 6 seconds. So essentially for the same time after 6 seconds, we are looking for the distance, which is the arc length. So we are asking, what is S? Okay. Well, I can just utilize my formula. My arc length is equal to my radius times the angle carved out. My radius is 10 centimeters. My angle is pi over 3. So this would be a distance of 10 pi over 3, and my unit is the same as my radius. It is centimeters. Since my directions didn't say to round, I go ahead and leave this as is. Next up, I want to now find the linear speed of my point P in centimeters per second. And again, you can use either of these formulas, but your speed is equal to your distance over time. And in our case, the distance is the arc length, because that is what it's traveling. My arc length is 10 pi over 3. My time is 6 seconds. So this is really, if I go and rewrite this, this is 10 pi over 3 divided by 6. So that's times 1 over 6. These are both divisible by 2, so that gives me 5 over 3. So this would be 5 pi in the top, and then in the bottom, 3 times 3 gives us 9. And that would be in centimeters per second. Okay. So again, I like this method because distance equals rate times time is something you've seen before and makes sense. So it's just connecting all those dots. But to show you the other formula works, your linear speed is the radius times the angular speed. The radius is 10, the angular speed is pi over 18. Both of those are divisible by 2, so that gives you 5 over 9. So you do end up with exactly the same thing if you go to this equation. And again, although it's simpler, it is another formula you would then have to remember. So I'm not the biggest fan of going this route, but you absolutely can, okay? So again, lots and lots and lots of practice with evaluating your different trig functions at all types of angles now. Get practice building your unit circle. because if you feel comfortable with these, your graphs of all the trig functions, which we're about to go through, are gonna make a lot more sense.